Hey, my name is Ben Adler, and this is my working Stirling engine on the right. As you can see, it is spinning pretty fast. It is currently being lit by 3 candles, and as a Stirling engine, it effectively converts heat energy to mechanical energy. In order to turn heat energy into mechanical energy, Stirling engines rely on principles of thermodynamics, as they rely on the fact that gas expands when it is heated and contracts when it is cooled. In equation form, this is Pfeffer's ideal gas law, PV equals nRT, where R is a constant. What is important is that in a Stirling engine, otherwise known as an external combustion engine, all the input, heat, energy, is drawn from an outside source, and ideally, no air enters or exits the engine in the process. In other words, N, the number of moles of gas, remains constant. This diagram here is a Stirling engine PV diagram. On the y-axis is the pressure of the gas inside the engine, and on the x-axis is the volume of the gas inside the Stirling engine. This diagram shows what happens to the gas inside the Stirling engine over time. Let's start at point 1. At point 1, the displacer is at its maximum height inside the pressure chamber. Meanwhile, the diaphragm is at a neutral height. At this point, the air inside the Stirling engine undergoes isothermal expansion. That is, at a constant temperature, the air grows and takes up more space, at the cost of the pressure it takes up being less. So it gets to point 2. At point 2, the displacer is at a neutral height, and the diaphragm is at its maximum height. The air inside the engine is now in thermal contact with the ice on top of the engine. This causes the air to cool and undergo isovolumetric cooling. In other words, the gas inside the engine loses heat energy while at the same time staying at the same volume it was before. Now the air inside the engine is at point 3. At point 3, the displacer is all the way at the bottom of the pressure vessel, and the diaphragm is at a neutral height. However, the air is still in thermal contact with the ice on top of the engine. At this point, the now cold air undergoes isothermal compression. In other words, the now cold air's volume drops while its temperature remains the same. In consequence, its pressure rises. Now we are at point 4. The diaphragm is at its lowest point, and the displacer is at its medium height. The air inside the engine is now in thermal contact with the flame underneath the engine, causing the gas to undergo isovolumetric heating. In other words, at a constant volume, the temperature of the gas rises. The air is now hot, and the system is now in a position where the displacer is at the top of the engine, while the diaphragm is at a neutral height, and we are back where we began, hence the Stirling cycle. The Stirling engine cycle is very similar to the Carnot cycle, but they have a few differences. Aside from the fact that the Carnot cycle is purely hypothetical, the main differences rely on the pathways between 2 and 3 and 4 and 1. The phases in between 2 and 3 and 4 and 1 are adiabatic phases, otherwise known as isentropic phases. This means that the entropy of the gas remains constant. Because it is merely the entropy of the gas remains constant, volume is allowed to change, and pressure and temperature. However, in the Stirling engine cycle, the volume is held constant and doesn't change. This is the maximum theoretical efficiency any heat engine can have. It must be less than 1 minus the temperature of the environment over the temperature of the energy that's being inputted. Theoretically, the only type of engine that could actually equal 1 minus Tc over Th is the Carnot engine. Although Stirling engines are not quite as efficient as the hypothetical Carnot engine, Stirling engines are very efficient for heat engines. While most internal combustion engines, such as gasoline engines, run at an efficiency of around 20 to 25%, Stirling engines can run at efficiencies up to 38.5%, which were found in the 1980s. While my Stirling engine probably does not run at its maximum theoretical efficiency, this inefficiency is likely to be caused by friction, as well as the fact that we're not running in a 0 Kelvin environment with a very, very high heat source.